Hello, welcome back, College Algebra. So we're doing section 4.2 today, 42 being the life, the universe, and everything. It's going to be the fun part of linear functions. Our big goal today, as you can see from the top, is to learn to build linear models using verbal descriptions. So being given a description of the equation, can you actually build the equation? Which, if you're like most algebra students, this is one of the harder parts of algebra. This is a combination of two of our favorite things in life, math and the English language. The second part is being able to model data using a linear function, which is the same basic concept, just being able to take that then description and turn it into a graph. So, the three greatest things in life: math, words, and pictures. I can already tell it's going to be a very fun day. Let's start off by talking about from the textbook on page 309 in the text, which is page 327. There's this little section here called Building Linear Models from Verbal Descriptions. It's honestly the most useful thing you will get from this entire chapter. I'm glad they put it at the beginning. And I'm actually going to copy this entire section into my notes, and at least in shorthand, because a lot of these pieces really need to be known, and this gives us a great pathway to finding out how to do these problems. If you can follow these steps from beginning to end, you can be able to take most any problem and at least have a good idea of where to start. And then going from there, it's about can you answer each question in particular. So let's start with the first thing. 1. This is again on page 309/327. And since I know many of you guys like to see the homework, your homework tonight, those of you guys that want it right away, is page 317/335, 9 through 55 odds. And this will again be due on Saturday, just like this week's. So page 317/335, 9 through 55 odds. And I'll put that in the description in the homework assignment as well. Okay, number 1. When it comes to being able to build a linear model, one of the first things you know is identify changing quantities and then define them as variables. And if you can, use them as a picture. So, number 1, you want to determine what's changing. These changing values will become your variables. Oftentimes, they'll throw a bunch of what I like to call word salad. It's where they shove a paragraph of text in front of you and say, make an equation. You got to be able to sift through those words and be like, okay, which of these are actually changing? What's describing and going on here? And how do those eventually become variables? Next is to be able to sit there and maybe use a picture to help with this. If you can't see what this is going on, if you can't identify what's changing, maybe a picture of it will help you to see, oh, if they're talking about going up a ladder, that just means a change in height. And so those kinds of things are really helpful, and they go great in combination with each other. So if you can determine changing values, you can determine variables, which can help you understand the picture better. Or if you can understand the picture better, you can go backwards and figure out the other pieces. Okay, 2. You need to carefully read it to determine information. This is kind of one of those dull things. But the big one here is you want to be able to determine values such as slope and initial value. When it comes to a linear equation, remember, most linear equations are going to have the form y equals mx plus b for a lot of these problems, or variations on it, such as the point slope form, y minus y1 equals mx minus x1. With this information, if you can determine the slope and the initial value, you've got this equation pretty much on lockdown. And so you need to be able to be carefully reading the problem and seeing, okay, what changing is typically dealing with slope. And what values you're dealing with are typically initial values, or values that come in terms of points. And so carefully to sift through and read each part of the problem, try to determine things like, where do we get these values from? And with part 3, the big thing here is to interpret. I can't spell interpret, of course. You need to interpret the values. Like if they say a number like 35, really they didn't say 35, because it could be positive 35, it could be negative 35. In any given problem, you have to have context. And there's words in the problem that will try to dictate and tell you what does this value actually mean. And sometimes those come from the picture. Like if I, for example, describe a skier from the previous homework assignment going and going skiing. If you've never been skiing before, you typically start at the top of your ski and go down your hill. Well, if I look at this scenario, then my rate of change is going to be negative because I'm going down the hill, and down is always a negative value. My initial value is going to be a positive number because I'm starting above ground and coming back to the ground. If I'm above the ground, that's a positive number because we're above. Above means positive. Although we're going down over time, we are sliding down. That means we'll have a rate of change that is negative. And so being able to look at these in terms of a picture and seeing how these can fit together can allow us to interpret that information and say, okay, I've got a number now. Is that a positive number? Is it a negative number? And what clues in the problem can give me context to that information? Okay, next. If you're not sure about the formula, because this information is good for pretty much any problem. It says it's for linear, but you can follow this formula through to figure out a lot of other more advanced problems. And if I'm doing an advanced physics problem, where I'm not 100% sure what information I am given or how to find it, I can often use things like number 4, where it talks about, checking and tracking units. That kind of thing is a big hint when it comes to physics, because a lot of physics problems have very strange units. And so if you can figure out how the units kind of fit together, then we can determine exactly which piece will tell us how to find the formula. In fact, there's some cool formulas that you can prove work just by looking at their units. So that's a really fun one that you can try sometime if you're looking at it for number 4. So you need to determine a pathway, which means you need to find a formula. Things that can help you with this are to look at the units. Units are a big helpful key to this. Because, for example, if I know I'm looking to get a distance, if they give me a rate of change like feet per second will never give me distance because I've got seconds in there. That's not a distance. Distance is defined just by the feet. So I need to find a way to get rid of the seconds, which can be done by multiplication. And so looking at things like units can be very helpful to figuring out that you have your pieces in the right place. The same example from last week. In fact, I'll scroll up to it for a second. This was, I believe, the very first problem we had last week from this assignment. Oh yeah, number 1. Terry's skiing down a hill. Terry's elevation in feet per second is given by this formula. Write a complete sentence how to describe what's happening. Well, if you look at this information, if I know I'm doing 70 and I've got 3,000, the 70 is my rate of change, which in this case, it tells me it's in feet per second. My 3,000 is in terms of feet. These have different units. I can't naturally put them together. That's why in the problem, you'll notice that the formula doesn't try to put them together until it makes some very specific change, t. I can't put together feet and feet per second. They're different units. But because the feet per second is multiplied by time, it's going to make the seconds disappear, leaving just feet and feet, which we can put two things together as long as they're the same unit. And so information like this comes from the units, and we can determine exactly how this thing is changing over time and how we get the information just by looking at these pieces. I can't put together feet and feet per second, so I have to use a variable to change one of them so I can put them together. Okay, going back down to our section. Number 5. All right. Okay, if needed, write out your formula. You don't always need to write out the formula. Sometimes the formula is just to help you. It's just there to showcase kind of which pieces you need, and really you can kind of start going and using it. But it is very helpful to always write out your formula to see exactly what components you're going to see in case you've missed something previously. Because if you know the formula you're supposed to use based upon the pathway you're given, you can determine and say, oh, did I miss maybe an initial value that I need? Or did I maybe miss out on the slope? There's all kinds of information that can be very helpful. And so having those pieces, super convenient. Make sure, if you can, write out the formula. Only if necessary, though. And you decide for yourself when that's the case. Number 6, solve or evaluate the function using the formula. So this is my solve. This is usually also my rewrite, if I need to. If there's more than one variable involved, maybe I can get rid of one of them. Maybe there's something in the problem that says, hey, that piece, I can get rid of it using some fancy technique in math. But I know that's always going to be a possibility. Now, in any given problem, these 6 steps so far, you could end up doing all 6, or you may end up jumping around and skipping some of them because you may not need all of them. You have to make those choices and see where your problem goes. But if you ever find that you're not getting the answer you want or missing a piece from the solution the text of the book has, you may consider going back and checking, did I actually do all the parts to the first step? Did I actually do all the parts to the second step? Did I do all the parts and continue from there? All right, 7. Reflect on whether your answer is reasonable. And this one's the big one for me as a math teacher. Because sometimes you can easily check to make sure if you got the right answer, if it makes sense. If we look at this example with the person skiing, and let's say you were asked to interpret this problem, and you said, well, this is going to be 70. And you may be very logical in saying, well, I chose 70 to be a positive number because, well, I just, thought he was going up the hill. But if you're looking at from a realistic standpoint, it makes no sense for him to go up the hill when skiing. That's not really how you do that. Now, part of number 7 is you have to understand the context of the problem. If you don't understand what the actual situation is, answering whether or not it's reasonable is almost impossible, because you don't have enough background information to be able to answer that question of reasonability with any degree of certainty. So you may want to sometimes do some research if you're not entirely sure, especially if you've got the time. Or it's, let's say you actually have a real world problem where you want to see if your answer is right. It should make sense that we can check our results based upon what we know. And that's the reasonable part of this. All right, 8. Clearly convey your results. Make sure you use appropriate units. In this example, it would make no sense if I put this in terms of miles, because everything the problem mentions feet. It just doesn't make any sense. And this is the part that I struggle with the most. Full sentences, if necessary. It's very common in mathematics to be like, the answer's x equals 4. Yes, I did it. But really the answer is more like, hey, at 4 feet, these values are going to be the same. Because that's really what you want. Saying x equals 4 is true, but it's not really the answer the person is going to work with. If you're truly doing a mathematical problem or working with non-mathematical people, the common thing is to say, well, the answer is 4. And then that same person will look you in the face and say, I don't know what that means. If a friend of mine is working on his car and he asked me to come over and help, and he says, I need a 10. And I looked and I was like, what the heck do you mean you need a 10? Like, 10 tells me nothing. And he was like, oh, I need a 10 millimeter socket wrench in order to fix this part. That makes sense. With more context and more information, the results that he's giving me, what he needs, makes more sense, and I can help him to get to that solution. But without the results, if he just says 10, I have no idea what the heck that means or how to help him with it. And so having context with the clues to say, yes, this is the answer, but it needs to have units along with it, and full sentences, if necessary, to convey what it's describing, it just goes back to being reasonable, to make sure you actually have the right solution. Each one of these all fits together very neatly and tightly. If you end up being weak on one of these areas, there's a good chance you'll either get the wrong answer if you mess up on steps before it, or you get an answer without any context, which means that the person who's reading it, if they don't see the problem, they don't understand what your solution means. If, for example, I go up to here and I say 12 on the skiing example, and it's like, okay, well, what's the 12 mean? Well, maybe 12 is where he hits the ground. Like maybe 12 is where he runs out of a hill and he runs straight into the ground. Or maybe 12 is how much time it's going to take for him to get to his top speed. Maybe 12 is some other factor that we don't know. Maybe at 12, there's a tree that's randomly sprouted in the middle of his path. Without more context, There's no information to tell me what 12 means. There's no information to tell me what 4 means here. There's no information, no context. The answer is meaningless. And so for a lot of problems, this last step is going to be the hardest one to get used to again. Because so much of the time we focus in mathematics about give me an answer, I want an answer so I can compare. But if I don't understand what the answer means, then the answer isn't really useful. Okay, this is the majority of my notes. I only have a couple more things to add before we go on, so let's go ahead and get to those. First, some things to help out here. Key phrases, words. Since we're dealing primarily with linear problems, one of the biggest things to talk about is how do we find things like slope. Now, in a given problem, slope is defined as the rate of change. It's how much something is changing over time. And in the context of a problem, what you want to look for is how does the word change indicate slope. So let's take a look at an example here that is given in the textbook. Right here at the top. Emily is a college student who plans to spend a summer in Seattle. She saved $3,500 for her trip and anticipates spending $400 each week on food, rent, and activities. The rest is, dictating the rest of the problem. The big pieces there are understanding that we've been given two numbers. We've been given $3,500 and $400. Now, these two represent the two primary pieces you want in a linear problem: the slope and the initial value. These two pieces, one of them is going to be the slope, one of these is going to be the initial value. The question is, how do you determine which is which? And moreover, 3,500 isn't very much information. Is that a positive 3,500? Is it a negative 3,500? Is it a positive 400? Is this a negative 400? Without more context and information, it's not always easy to tell. And many of you guys can look at the problem and say, I understand what it's describing, but being able to take the description here and put it into some kind of formula, that's harder. So let's look at some context clues to figure out what these numbers mean. So, this first example, they've listed out the different steps you take in order to determine which piece goes where. In this case, they've defined a variable, m. They said m is going to be how much money Emily has. M compares to t, the amount of time she's going to spend while she's in Seattle. And to people like you and I, we might look at that and say, well, she's going to spend an unknown amount of time. That doesn't make any sense. But you got to keep in mind that for this example, we're just trying to understand the basic components of it and see how it fits together. So, time in this case is your input. It's not what's changing. Time is constant. The output is how much money she has. Because in the first week, how much money she has is different than the second week, which is different than how much she has during the third week. And so as you see for these problems, it's important to understand what kind of variables are you dealing with and how those variables fit together. In this case, we're using m for money and t for time. So we're going to have an equation that contains m and t as variables. Now the question is, what fills in these little blanks here? What goes in each of these places to determine the type of value we're going to have? And the trick is, these two numbers are going to go there. The question is usually how. Okay. So there's some context clues here. It mentions in the problem that she has $3,500. $3,500 in this case is an initial value. Now, the word initial value is typically seen in physics. In algebra, we have a different name for it. It's called the y-intercept. The initial value is a physics term that just means the y-intercept. And so, in terms of my original equation, b is my initial value, which means that this 3,500 needs to be separate from the t. Because remember, t is the variable. It's our x in this case. And so my t needs to have either an addition or subtraction sign that separates out this $3,500 from everything else. Now, in the context of the problem. She has 3,500. She doesn't owe 3,500. Owing somebody means you have negative money, but having that money means you have positive money. If you ever had a bank account before, you understand, if you ever look up online, money you're putting in, money you have, is always positive. Money that's being taken out is always negative. Now, what's that mean for this 400? Well, each week she's spending $400. That's an indication of which sign we're supposed to use here. The initial value is how much she has is a positive 3,500. But each week she is spending 400. Spending means she's taking something away. She's losing that money. And so that tells me that in this context, it should be negative 400. In the original description of the problem, it doesn't say negative 400. Right here, it just says spending $400. Up here, it says saved $3,500. It doesn't say positive 3,500. It doesn't say negative 400. We have to use the context of the problem to make sure that this answer makes the most amount of sense. And in this context, it does. We start out with $3,500, which means that in the first week, that's when time would be 0. We would have $3,500 in the bank. Making a table here to help illustrate this. I have my time. I have my money. So when we start off, that's at time at 0. We have $3,500. Well, at the end of the first week, she pays her bills. Week 1 is done. She's only going to have $3,100 left. Because I plug in 1 for t. Negative 400 times 1 is negative 400, plus 3,500 is 3,100. At the end of the second week, she spends another 400, means she's at 2,700. And so you can see that it matches this form. The initial value is also the y-intercept because it has the point 0, 3,500. Whereas these other two represent other values. This first one is at the first week, she has $3,100 left in her bank account. At the end of the second week, she has $2,700 in her savings account. You have to be able to interpret the data and understand that this coordinate, 0, 3,500, means when she's starting, she has 3,500. This second coordinate, at 1, 3,100, means after the first week, she has 3,100. This 2 means after the second week, she has 2,700. It's not enough to be able to be like, answer. You have to be able to interpret it. You have to be able to understand this value means something. Without that indication, without those means, there's no way to understand or comprehend where this information comes from. It just becomes a number. And while numbers are cool and fun and interesting for people like me, they're probably not the best for you guys. It has to have context, otherwise it's meaningless. So, when it comes to slope, rate of change, if they mention increasing, decreasing, going up, going down, if they say leaving, a lot of verbs are used to determine things like slope. If you look back to the original problem, it says here, anticipate spending. Spending means that money is changing, right? If I say I'm spending $10, it means I'm changing my current wallet to have $10 less. As weird as it sounds to put it that way, that's really what it means. And so having those verbs, or maybe English people, someday, please help me. Having these changing words indicates that we have a rate of change. Indicates that 400 is related to the rate of change, meaning it's related to the slope. But we still have to take the time to interpret, because if we have these two different words, these have different meanings. Increasing would indicate positive values. Decreasing would indicate negative values. Going up, positive values. Going down, negative values. Leaving would indicate negative values. Coming in would indicate positive values. In the context of a problem, it will often be necessary to read some of the phrases and say, like, okay, I'm given numbers, what do they mean? Because we could have easily looked at this and said 3,500 and 400 as dictated in the problem. The 400 and the 3,500, that could be a point. Without more context, it's just two numbers, and two numbers can fit into a lot of different categories. So it's important to note things like, how do we determine a slope? What keywords tell you that this is supposed to be some kind of slope? Okay? Initial values. That's the other part. What kind of keywords or ideas can tell you that you have an initial value? Okay? Well, you look for phrases like starts with. Okay? In this example, saved, began, indicating some kind of starting place is usually an indication, or if they list a year, specifically the first year they list, and say, oh, this first year we had this much money, well, that's an indication that that's the initial value. In this case, your B value from the original formula. And so having that information can dictate to you when we have these big details, these big pieces that need to then fit together so we can determine the exact type of problem we're dealing with. Okay. For the next piece, let's go ahead and continue down for our textbook. They have some great examples in the text for this chapter. Many of the problems in your homework tonight pull directly from these examples, so if you need some extra assistance with some of these problems before Saturday when I answer questions, please feel free to look in the textbook. It does have some great resources. Please use them. Again, a lot of the pieces we need to talk about are specifically pulled from page 307, that first page, or sorry, page 309. They reference that page a lot in this text, for this section in particular. Use that information. And again, make sure we've got homework listed, page 317/335, 9 through 55 odds. Okay, next piece. Given a model. Okay, let's take a look. Suppose, for example, that Hannah plans to pay off a no-interest loan from her parents. The loan balance is $1,000. She plans to pay $250 per month until her balance is zero. That information gives you context to how the rest of these pieces are supposed to fit together. Okay? So, she mentions the phrase loan balance. If you've never taken out a loan before, you're not... well, good for you, first of all. As you get older, that becomes a little harder sometimes. But if you haven't ever taken out a loan before, you have something called the loan balance. This is always a starting value. This is how much you take out. In this example, she says that starting value is $1,000. Now, she then says she plans to pay $250 per month. Notice it says $250 per month. This per month, this phrase, indicates a change. Because each month she's making a change to the value. That value is changing by 250. So this tells me that this is a slope. And so I have a starting value and I have a slope. I can write a linear equation for this problem. My linear equation, in this case they use f of x, is equal to, we have x, and then your initial value. So remember, our rate of change goes with the x, so that's 250. Our initial value is the b, so that's 1,000. But then we have to answer the second part. Are these positives or negatives? Well, since she's starting with this money, that means it's a positive number. Even though it's like a kind of, it feels like it could be negative, because in the context, like she owes $1,000 to her parents in this case. In this case, she still has $1,000 in the bank, so she still has the money. It's still a positive 1,000. And how much she's paying off, well, that's going to indicate that this is a negative. Because she's paying it off, how much she pays is going to go down over time. If it asks the question like, when will she be out of money? Or when will she stop owing money? If we ask a question like this, being able to interpret this equation is really helpful, because we can look at this equation and see, well, answer basic questions. After so many months and how much money is owed, you can see that when she starts off, she owes $1,000. However, after the first month, she only owes $750 because the number she had went down by $250. In the second month, $500. In the third month, $250. In the fourth month, $0. And so to ask, when will she stop spending money? Well, when x equals 4. But that's not enough information. Instead, we got to look at it and say, she will be paid off after 4 months. It's not enough to just write down x equals 4. X equals 4 means nothing. Because if you have no context, then 4 could mean 4 months, 4 could mean 4 years, 4 could mean 4 decades, it could mean 4 cats. After 4 trips to France, she'll be paid off. Who knows what this 4 means? Without context, 4 is meaningless. And you can't get that without telling the person that's reading it. You should always write your answer as if somebody has read the problem but didn't really understand the problem. You should always write it that way. Because, well, that's kind of how math people view everybody that doesn't do math. We always understand that some people are going to read it and not understand it. And so you have to write your answer in a way that makes sure that they fully understand. Hey, she started with $1,000 that she owed. She paid $250 per month. After 4 months, she'll be paid off. Anybody who has zero math background can still understand what we just said. And that's important. Now, how do I get that same answer with an equation? Well, in this case, they used it by doing what's called an x-intercept. So we talked before, going back, about initial values. These are also y-intercepts. Okay? You're looking for keywords and phrases to determine when you have a y-intercept and how to put that into the equation. We talked about slope and how you can determine rate of change and keywords or phrases that can indicate when we have a slope involved. But there's one other major part of linear equations that tends to happen a lot, and these are x-intercepts. X-intercepts have a slightly different meaning. When it comes to an x-intercept, these are when your output is 0. Because remember, your x-intercept is when y equals 0. But remember, y is an output, so it's when y equals 0. When can this happen? It's important because x-intercepts by themselves, I can see in a picture what an x-intercept might look like. If I have a graph like this, I can see in the picture, oh, here's an x-intercept. But what does it mean? Like, what does that dot on the picture actually mean? Well, this could represent, in some situations, when you are out of money. If your function is a money function, like this problem was, then your x-intercept is when you're out of money, or in this case, out of money owed. If it's a height function, it could be the ground. Like if we go back to our little ski man example, right? Our x-intercept is when he or she hits the ground. And so you don't have any context until you understand it in that form, because x-intercept is just a number, right? It's going to give me a dot on this picture, but I can do more with that dot. You know, it might represent out of money. It might represent when you touch the ground. It might be, for example, like the stock value. You know, when does your value crash? You know, if your value is hitting a value of 0 as an output, that means that your stock value is 0. It's really bad. You know, this could also be when you've sold out. If it's a stocking question, like, oh, we have 30 cases of soda in the store. You know, we sell this many cases per day. This will indicate when you sell out of cases. And so the x-intercept can indicate a lot of consequence. The y-intercept indicates initial value. The x-intercept indicates long-term consequences, like what happens later on down the road to determine when exactly this function ceases to work as well. Because in terms of linear and realistic function, negative values are not as common as they used to be. You know, in this example, these negative numbers, if I'm talking about, stocks of soda. I can't have negative stocks of soda. Like, that should never be down here. And so this dot, this x-intercept, can indicate when something massive needs to change. Okay. So that's the next big piece. And it can be found in one of two ways. It can be found by a graph. It can be found by using a table. It can also be found by letting y equal 0. Or letting f of x equal 0. So you can see in our example here how they did that. They took the equation, which was negative 250 x plus 1,000. And they let the f of x part of the equation equal 0, and then they started to solve it. They moved the 1,000 over, or in this case, they moved the 250 over. And they divided both sides by 250. Like, this process is how you determine an x-intercept. You take what was once f of x and replace it with 0. The y-intercept can be found by the opposite process, of course. When you look at the y-intercept, it's when the x value is 0, as we saw from our little table here. When the x value is 0, when the input value is 0. Because remember, our t in this case was the input value, what we were plugging in. And so that indicates that that's the original value. That's when x is 0, the input is 0, when t is 0. That's our x-intercept. Our y-intercept is simply the other way. Okay. Next component. I love these little how-to boxes. If you haven't seen them in the textbook, you need to read some of them. It's great to help out if you don't know the steps, the methodology. This little piece right here, it's in the textbook. It is on page 311. It is so helpful to figure out, okay, what are my steps? So, if you want to know what the steps are to solving a lot of these problems, look on page 311 in the how-to box. Okay, it showcases exactly which steps are really good, and if you look really close, you might notice that most of them are the steps we did in the last section. We didn't change topics. We're now just looking at them in terms of more word problems. So, 1, identify input and outputs. Those are just x's and y's. 2, convert the data to coordinate pairs. We did that. 3, find the slope. We did that with the slope formula. 4, write the linear model. We did that using the point slope form and the slope intercept form. 5, use the model to make a prediction by evaluating, so that's plugging things in. 6, use the model to identify an x value that results in the given y value, so that's analyzing results. And 7, make sure to answer the question. This is why you have that last piece of putting it in complete sentences. This how-to box, if you message me on Saturday saying, I don't know how to do this problem, I'm probably going to screenshot this page and say, hey, did you check this out first? Because it really is the best way to do it. And if you then are still confused, I'm probably going to do this one step at a time. And be like, okay, let's do step 1 together and answer these parts. Let's do step 2 together and answer these parts. So, let's go ahead and list them out so we make sure we have them for our notes. 1, identify inputs and outputs. It's important to answer the previous questions from the previous pages for things like what are the variables in those pieces, because if you know the variables, it's easy to tell what's an input versus what's an output. 2, once you've got your input and outputs, convert to data points. 3, find the slope. How do we do that? Do not forget the slope is the slope formula, which we use 2 different variations on. The y2 minus y1 over x2 minus x1 is the first one. This is the one from Algebra 1. The more advanced one, using functional notation, is also perfectly acceptable. There we go. 4, write the linear model. You may want to use slope-intercept, but it's far more common to be forced to use point-slope. It is far more common to be forced into this one. Remember, you can always use this one and then back solve for the top one. So it's always an option to go backwards if you need to. Step 5, use the model to make predictions. Step 6, use the model to identify x's given y's. It is common for me, because I'm not a fan of equations, I actually like tables. Tables are nice for me. It is common for me to use this linear model to make a table, and then use a table to predict x's and y's together. Then step 7, make sure to always answer the question. Use your words. I had a terrible teacher that I absolutely hated when I was in middle school, who used to yell at us every time using the phrase, use your words, because we'd always raise our hands and be like, x equals 2. And she would just look us in the face and be like, no, use your words. You are better than that. You can't just say x equals 2. In this case, that's how we got to do it. Okay, there's some great examples. I'm not going to do these examples with you guys. I think they're great to look at. Please take a look at them. Okay, they're very helpful to walk through this 7-step process. What I want to make sure to get to is understanding the next piece, which is specifically dealing with when you have more than one equation. Okay, when you have more than one equation, you have to kind of approach these problems just a little bit differently, because there's a couple different things that can happen. For each of these, you want to follow the same basic steps. So again, look at your how-to. This how-to is on page 315. Step 1, you want to identify the inputs and outputs. Use those inputs and outputs to find the slope and the intercepts. Okay, 3, set the two linear functions equal. And solve. Alternatively, you can also find the point of intersection on the graph. That's not a graph. Graph. Now, when you do these steps, there are 3 major possibilities depending on whether you're dealing with the picture in terms of the graph or whether you're dealing with an equation. So let's look at all 3 of them. All right. For this one, I'm going to ask you guys to use some outside information here. My first equation versus my second equation. If it's like most problems, your first equation, drawn here in red, versus your second equation, drawn here in my blue, it's a little dark bills there, you'll have one place where they cross. This indicates you have one solution. A single point of intersection. In terms of what that looks like for the equations, let's say you actually do the equation version, you'd usually get like x equals a number. Okay? This is most common. When you're looking at 2 equations, doing a system of equations, it is most common that these 2 equations will have one place where they cross. And you can see in the picture here that that's exactly what's happened. Right here. You have the first equation here, you have the second equation here, they've crossed in one place. in terms of the solution, that's usually x equals a number, which indicates that this x value is the place where these two functions cross. Okay? This is the place where they have the same output. So you would say these have the same output. So when x equals 2, these have the same output. When x equals 5, these have the same output. That's all this equation means. That's all this picture means, is they have the same output. Now, there's our second example, where the two happen to overlap. Okay? So in this case, we're dealing with some overlap. What does this look like in terms of the equation? Well, this means we have infinite solutions. How does that equation look? It really means you have, when you're finished, you'll have one number equals itself. So you might have 3 equals 3. The x's will, in other words, disappear entirely. So in the first problem, you have x equals a number. But when they overlap like this, the x's, when you solve them, will completely disappear and have just 3 equals 3, 5 equals 5, 7 equals 7, negative 2/3 equals negative 2/3. You have a number equals the same number. Anytime that happens, this indicates that you have overlap in your functions, meaning you have infinitely many solutions, meaning they always have the same output in all places. So, in this example, this will have one solution, x equals a number, and means it has the same output in exactly one place. The blue function and the red function have the same answer in one place. Whereas in this example, the red function and the blue function are essentially the same, meaning that you're going to have infinitely many solutions, the same output in all places. There's one last possibility. This was the hardest to draw correctly because people always judge by drawings. Good enough. So this means there are 0 solutions. This usually happens when you have a number equal to a different number. You might end up with 5 equals 7. You might end up with 0 equals 2. Like the two sides don't match. The x disappears in both of these examples. The x will disappear. But in one example, you have a number equals itself, so like 3 equals 3. In the other example, you might have like 4 equals 8. And when they are not the same number, this indicates you have no solutions. In other words, these never have the same output. It never happens. So anytime you're dealing with equations, like there's only 3 basic possibilities. Whether you do the math or whether you're looking at the picture, you could get one answer, x equals a number, indicating that there is one place where both of these functions are the same. Notice that over here, the red value gives you a lower answer than the blue value. Over here, the red value gives you a higher answer than the blue value. But in only one place are they exactly the same. In the middle one, the red equation and the blue equation give the same answers every time. That's why they have the same answer. That's why they're equal to the same number. That's why there's infinitely many solutions. And then over here, you can see that there's never a time when the blue and the red give the same answer. The blue is always above the red. The red is always below the blue. Since they are never going to meet up, we'd say they never have the same solution, which is why there's no solutions. There are 0 solutions. And so when it comes to building these models, it's important to note that anytime you're looking at the function, you have to be able to interpret the result. Being able to draw the red line is one thing. Being able to draw the blue line is a different thing. But being able to look at both of them together and say, one answer, and I know what that answer means. Or you want to look at the problem and say, the same crossing each other, infinitely many answers. Or never crossing, 0 answers. And to know how those two things fit together, that's a really big deal. Now, this should pretty much wrap us up. Yep, there it is. Remember our homework assignment? Our homework assignment for this section is going to be page 317/335 in our textbook. 9 through 55 odds. This is section 4.2. Make sure, if you haven't already done so, make sure I get that homework from last week. I will be accepting it up until tonight because I will have not started grading it just yet. And I want to make sure to get the grades in so people can get adjusted grades. Last thing I will say, this is a dual credit class. If you are not turning things in, your grade can and will go down. While we have said in our talks to all the students that we are allowing other classes to maintain grades, in AP and dual credit, you are still responsible up until the end of the year because this is a college level class. You are still responsible for turning in your work. So make sure you get your work into me. We will be looking at the last section on Wednesday. That is section 4.3. I'll be answering any questions on Friday as well as handing out a review. Over the weekend, we will likely have our first take-home test because this is a very short chapter. So make sure you're not falling behind. Make sure you're looking at these sections. And make sure you're coming in asking questions or shooting me a message when you need help. I will be available on Friday to answer any questions as well as to hand out the review. And then on Friday night, I will post a test. So let me know what you guys need, and I'll be there to help you guys out. Thank you, and I'll see you guys later.